Hello. Next paper ID is 7088. Prafulla sir, are you there?
Yes, sir. Yes, sir.
Yes,
Good
sir.
morning, sir.
Good morning. Good morning, sir. Good morning. Very good morning.
Hello, everyone. My research topic is optimal performance of cyclic coded orthogonal frequency division multiplexing system. These are presented by myself, Prafulla Gawande, along with the Kailash Karande sir and Hariram Chavan sir. Let us see first what is OFDM. OFDM is a digital multi-carrier modulation scheme that extends the concept of the single subcarrier modulation by using the multiple subcarrier with in same signal channel rather than the transmitting the data stream on a single channel. OFDM makes the use of number of subcarriers. Let us see the highlights of the OFDM. In the OFDM, the channel is divided into the number of subcarriers. That subcarrier may be 64 subcarrier or 128 or 256 or 512 like that. So the OFDM channel is divided into the number of subcarriers. That's why it is called as a multi-carrier modulation technology. This OFDM also supported to the high data rate and the bandwidth utilization in the OFDM channel that is very efficient. And that's why the OFDM technology that is used in the broadband wireless communication system like LTE, then WiMAX, and the 4G and the 5G also. In the OFDM, the subcarriers are the orthogonal to each other. Now, when you are talking about the any communication system, the channel performance that is very important. And the performance of the channel that will be measured in terms of the data rate or it may be measured in terms of bit error rate. But the channel performance of the any communication channel or the OFDM channel that will be degraded by the some factors. So such like error rate, IPAPR value, and the inter-symbol interference, atmospheric attenuation, inter-carrier interference, transmitted power per carrier. These are the factors which are affected on the performance of the OFDM channels. If you want to enhance the performance of the OFDM channel, we have the different techniques like coding, that is a channel coding, and the next is the adaptive power control of the carrier subcarrier, adaptive modulations, means the modulation is changing with respect to the conditions, and then the reduce the PAPR. In our research work, we are basically concentrate on the coding and the reductions of PAPR by using the coding. And for the coding, we use the cyclic code. So what is the PAPR? The PAPR that is nothing but the peak to average power ratio. Peak to average power ratio, and this power ratio that is very high when the subcarriers are in the same phase. And if you want to calculate the PAPR, we have the mathematical formula that is given here. That is a PAPR, that is a PAPR of the signal that is equal to maximum power of the carrier divided by the average power. Now, to reduce the PAPR, we have the different techniques like the clipping and filtering, partial transmission sequence, selective mapping, non-linear comparing transform, tone rejections, tone injections, and coding frames. In our research work, we are used the coding scheme to reduce the PAPR and find out the optimal performance of the OFDM channel. So why I am selecting the coding scheme? So that is why I am selecting the coding scheme, because the coding scheme requires the very less power, and the implementation complexity that is also low. Bandwidth expansion, that is the one major disadvantage of coding methods. But even if that is will be compensated with the that is data rate, and the BR degradation that is nearly close to 0 here in the coding rate, because the coding method coding has the capability to reduce the detect the error and correct the error. So we have so many methods: clipping, coding, and PTS, SLM, the NCT, TR, and TI methods. These are the methods. And in the coding scheme, where you use the cyclic code for the in our research work. And when you are implementing the our WebDM system, where I'm used the MATLAB 2010. And when you are implementing this WebDM system, I designed the WebDM transmitter, then the channel. The channel may be MIMO channel or SISO channel. And then again, and design the receiver also. And when you are designing this system, I am keeping some parameters of OFDM, that is a dynamic. For example, cyclic prefix, that may be 1/2 or it may be 1/4. I will maybe keep as a 1/8 or 1/32, like that. Similar way, this program or this model will be supported to the number of subcarriers, different number of subcarriers, that may be 64, 128 or 256 and so on. That maybe goes to up to the 2000s. No issue with this model. Then the similar way we have kept some other parameters, like ISI reduction method, zero padding or cyclic prefix. Then the channel encoder and decoders, and then the coding rate also the dynamic, that may be 1/2, 1/4, or it may be 0.5, 0.75 or 3, like that. Then the delay in the channel, that was also the dynamic. Delay in transmitting delay, that also the dynamic, because this is a simulation model. In that case, we need to define the delay also. So this is also dynamic. Now, if I want to calculate the optimal value of the EB by N0 or for the minimum PAPR and the bit error rate. So how to find out? I want to show the result of that. See here, in this case, the modulation type, that is a form 16, and then the channel type, that is the AWGN, additive white Gaussian noise channel, that is a Gaussian noise channel. And then we have a ISI reduction method, we are using here zero padding. Then the channel code, that is a cyclic code, and the method of the channel, that is a channel type. Actually, this is a channel type, that is a SISO, that is a single input, single output. And then the coding rate, that is a 0.75, and the input symbol length, that is 3, and the coded symbol length 4, and then the NFFT, that is the 128. That means the number of subcarriers, that is 128 here. And these parameters are constant, and what is the EB by N0, that would be vary here. On the 16, here this is 16, and on the EB, when the EB by N0 is equal to 16, at that time we are getting the minimum BR and the minimum PAPR. That I want to show by using the graph. Here. So in this case, I'm used the cyclic code and coding rate, that is 1/2, and the modulations, that is a QPSK, and number of subcarriers, that is equal to 64. So when you observe the optimal BR graph, the BR graph that will be decreasing when you are increasing the EB by N0. Similar way, PAPR, when you observe the optimal PAPR graph, in that case, the PAPR is a random thing here, random. And both are minimum at the 25. When the EB by N0 value is equal to 25, at that time, we are getting the minimum PAPR as well as the BR. So if I use the EB by N0, EB means that is the bit energy. If the bit energy is equal to 25, if you consider the N0 is equal to 1 ideally. So in that case, we are getting the better performance of the channel. So in that way, we are getting the optimal value of EB by N0 as well as the optimal BR and then the PAPR. Now this graph shows the optimal EB by N0 for the minimum PAPR and the BR with respect to the modulations when the NFC is equal to 64 and the coding rate is equal to 0.125. When you observe the optimal BR graph, first graph, then the optimal BR value that is decreases with respect to the modulation order. So for the COM64, that is very, very low. And when you observe the optimal EB by N0 value, that will be increases with respect to the modulation order, and the optimal PAPR is also increases. Now, in the second next result from the graph, it is clear that the BR value, optimal EB by N0 value, that is increases with respect to the coding rate also. And the optimal PAPR almost constant with respect to coding rate, almost constant. In the optimal BR value that will be increases with respect to the coding rate. So this is about the result. Then the next result that is related with the number of subcarriers. Here in this case we have calculated the optimal EB by N0 value with respect for the minimum PAPR and the BR with respect to number of subcarriers, when the coding rate is 0.125 and the modulation that is the QPSK. So when you observe this graph, then the optimal EB by N0, that value will be increases with respect to number of subcarriers, and the optimal PAPR, that value is also increases with respect to number of subcarriers. But when you observe the optimal BR graph, second graph, when you observe this graph, the optimal BR nature, that is a random here. So we are getting the minimum optimal BR value at the 128. Number of subcarrier is equal to 128. Now I want to conclude my research work and the research work from the experimental simulation result. It is observed that the performance of OFDM system is improved with the optimal values of EB by N0. The second observation, from my research result, at the optimal EB by N0, we have obtained the minimum PAPR and BR as compared to uncoded OFDM system. And when you're talking about the cyclic coded OFDM system, and this system is better at a low coding rate and the higher order modulation and less number of subcarriers for the optimal BR performance. And these are the references. Thank you. Thank you very much. Any questions, sir?
Okay, thank you, sir.
Okay, thank you.
Okay, thank you.
Thank you.